So in my last video, I talked about the fact that using IV curves, in addition to the power formula, P equals VI, that we can determine the minimum possible power requirement for a circuit. But before we're able to do that, we'll have to discuss Kirchhoff's current and voltage laws. Now, what exactly are those? Kirchhoff's voltage law is the idea that if you have multiple components between two known rails, and the voltage across all of these different components, the diode, the resistor, and the capacitor, the voltage across them will all be the same. What Kirchhoff's current law says is that if you have multiple elements in what's known as in series, then the current going across all of these is the same. So if you have 5 amps of current going through this diode, then you will also have 5 amps of current going through this resistor and 5 amps of current going through this capacitor. Additionally, say you had 5 and 0 here again, then we know that across this diode, if we have 0.5 volts, if we have 2 volts across this resistor, then we know that across the capacitor we must have 2.5 volts, because all of these voltages should add to 5 volts. Now, how exactly is that going to help us determine how to minimize P? Well, let's take a look at this example that I've set up. In this IV curve here, we have the IV curve of a resistor, which is this straight line, and by the way, this should all pass through the origin, and the diode, which is this exponential curve. And then over here, I've drawn a diagram for the IV curves of these two elements. So what I have set up here is that the voltage difference between the ground rail and the power rail is 5 volts, and we want to know how to minimize power. So if we know voltage is always 5, then this problem is essentially saying how do we minimize current? And in this case, we actually can't minimize current because we are already given a fixed IV curve, so then we will have a fixed I value. In this case, since we know that current must be constant, if we draw a dotted line across here, and then find these 2 points, we should find that these voltage values here add up to 5. So then we can just increment this dotted line up and down until we find where these 2 voltages would equal 5. However, we want to minimize power, and in order to do that, we need to be able to change something about this circuit. The easiest thing to change would be the resistor value. If we could increase or decrease the resistance, that would change the power value. So let's see what happens if we increase the resistance. So instead of having a IV curve like this, let's say the resistor has a steeper IV curve. Now what happens when we draw a dotted line in the same spot? Oh, we'll notice that the voltage coming from the diode remains the same. However, the voltage coming from our resistor has decreased, which means in order to compensate, we would need to raise this line higher, and then the current drawn by the diode would be much greater. So generally, if we have a circuit like this, a resistor and the diode in series, that means that increasing the resistance will result in the least power drawn. Does that mean we should just use a trillion ohm resistor? No, of course not. Because if we used a trillion ohm resistor, then say we have a light emitting diode here, which means we want it to turn on. If we have a trillion ohms, then there will never be enough current going through the diode to turn it on. So what is this aperture I have here? Well, I created this in order to measure the exact IV curves of all of these LEDs. So here I have 5 different LEDs that I want to measure. I have 4 resistors set up so that I can get 4 data points. This is just the breadboard that I will be putting all of these elements on. And right over here, we have the oscilloscope in which I will be measuring the voltage difference across the resistors. So let's try with this red LED first. Plug that in. So now I have my first circuit set up with a 330 ohm resistor. And right here on the oscilloscope, I am reading that this is giving me 3 volts across the resistor. Let's try another one. This is the 470 ohm resistor. And with this, I am also getting 3 volts. Hi guys, this is Future Wesley here, and you might be confused. How can we have the same results for 2 totally different test cases? And I was a bit confused about this too. And the reason is because the difference in voltage is extremely small. So I was reading all of these as 3 volts, when in reality, I should have been saying 3.01 volts or 3.03 volts. I eventually figured this out. After that, I tested every single combination of resistor and LED and recorded all the data on my computer. So here's a time lapse of that. So now that I finished recording all the data, I've put all the data points into decimals. Now does this look like anything familiar to you? Probably not. And it doesn't look like anything to me either. So let's change these a bit. Here I have recorded the voltage and the resistance. However, the voltage is across that of the resistor, and we only want to know what's across the diode. So what we would do is just 5 minus everything here. But actually before that, the number here is the resistance. However, we don't care about the resistance. We only want to know the current across the resistor. And recall that the current across the resistor would be the same as the current across the diode because they are in a circuit in series. So if you recall our equation V equals IR, since we have the voltage here and we have the resistance here, if we just divide the voltage by the resistance, we should be able to get I. So let's do that. So here in my calculator, I've put in the result of the first one. 3.09 divided by 330. Is this absurdly small number? And no one knows how to really make sense of this. However, there is one trick we can use, and that is because this value is in amps, we can use milliamps instead, which would be 1,000th of that. So we have the 10 to the negative 3 here. In milliamps, this would be 9.36. So let's put that into our decimals and do the same for all the others. Okay, so I've gone ahead and converted all the voltages and resistance to current. And now what I will do is take these voltages and do 5 minus this, because that will give us the voltage across the diode. So let me go ahead and do that. Okay, So now I've completed that, and if we scroll in now, does this look like a recognizable chart to you? The answer to that is probably still no. In fact, this doesn't look like a very good chart to me either, because in theory we should have exponential equations that pass through the point 0, 0. But none of these curves look like they will pass through the point 0, 0. For each of these, I will now create an exponential equation that I hope can semi-accurately represent the LEDs. And now I finally determined the IV curves for each of these graphs. Of course, none of this was necessary at all, because what I just did was I tested each of the lights and tried to get to the highest resistance possible, and I found that anything under 10,000 ohms of resistance is totally fine. And from before, earlier in the video if you remember, what we're just trying to do is increase the resistance to the maximum. So all I really had to do was just test the LEDs with resistance, with increasing resistance until I found one that I was satisfied with. But even though none of this was really necessary, I think it was still a fun practice. And although I am not going to be using any of this data in my design, IV curves are a commonly used tool in engineering. And the reason engineers don't necessarily always have to calculate things is because when we make measurements like I just did, the precision is not always perfect. Therefore, even if you have the perfect equations, you're never going to be able to find exactly what's happening in real life. It's just not practical. So engineers use curves like this to help them easily determine what values of resistance, capacitance, inductance, and many other things that they will really need in their circuits. So that's the principles that I'll be using in my next few videos in order to reduce the power consumption of this computer here. I hope you enjoyed. Subscribe, like, comment, goodbye.